So we begin this week by a brief problem session on the material which was covered in week 6 and week 7 of this course. So we start by looking at the first problem, wherein we try to write a given matrix as a product of elementary matrices. Okay, so let's begin. So problem 1. So let A be the matrix given. Let A be the matrix given by 0, 1, 0, minus 1, 0, 0, 0, 0, minus 1. Then the first one says find elementary matrices such that we can write as a product of these elementary matrices. Find elementary matrices E1, E2, E3 such that A is equal to E1, E2, E3. That is the first part of the problem. And the second part of the problem is to compute A inverse. So needless to say, the second part is actually simple corollary to the first part. So let's focus on solving this problem. Solution. So let's recall what our A is. If you recall, A is given by, let's just go up and check out what A was. 0, 1, 0, minus 1, 0, 0, 0, 0, minus 1, the rows of A. 0, 1, 0, minus 1, 0, 0, 0, 0, minus 1. So let's see what are the elementary matrix operations that we will be applying to A in order to get hold of A as a product of these elementary matrices. So the strategy we would follow is the following. Let us find E1 prime, E2 prime and E3 prime such that after doing a row reduction of A, we will get the identity such that E3 prime, E2 prime, E1 prime times A is the identity matrix. And then this would imply that A is the matrix which is given by E1 prime inverse, E2 prime inverse, E3 prime inverse. But we know that the inverse of an elementary matrix is again an elementary matrix. So this will just turn out to be, this is exactly what we want. This is the E1, E2, E3 that we want. And yeah, we will come to the inverse of A in the second part of the problem. So let's focus on this. So our immediate goal is to find E1 prime, E2 prime and E3 prime such that after the relevant row operations we get back the identity. So the first one I would say is to exchange these two rows, the first row and the second row. And what was the elementary matrix that was needed to exchange the first and the second row? So let E1 prime be equal to, so the first row and the second row. So this will be 0, 1, 0, 1, 0, 0, 0, 0, 1. This is precisely the matrix you need to multiply to exchange the first and the second row. So okay, so let's check what is E1 prime times A. This will just be 0, 1, 0, 1, 0, 0, 0, 0, 1 times our matrix A, which I think is 0, 1, 0, minus 1, 0, 0, 0, 1, 0, minus 1, 0, 0, 0, 0, minus 1. And after the multiplication, this will just turn out to be equal to minus 1, 0, 0, 0, 1, 0, 0, 0, minus 1. So we are exchanged the first row and the second row. The next is to multiply the first row by minus 1. So let E2 prime be equal to minus 1, 0, 0, 0, 1, 0, 0, 0, 1. And now let's check what is E2 prime times E1 prime A, which is minus 1 0 0 0 1 0 0 0 1 times minus 1 0 0 0 1 0 0 0 minus 1, which will just be 1 0 0 0 1 0 0 0 minus 1. So we are quite close now. And then let E3 prime be equal to, we need to multiply the third row with minus 1. So this is going to be 1 0 0 0 1 0 0 0 minus 1. And you can check that E3 prime, E2 prime, E1 prime A is equal to 1 0 0 0 1 0 0 0 1, which is the identity matrix. So we have essentially obtained what E3 prime, E2 prime and E1 prime is. So hence A is nothing but the matrix E1 prime inverse, E2 prime inverse and E3 prime inverse, which is quite straightforward to compute, because what was E1? Let's look at what E1 was. E1 prime was, well, I'll put it in green here. This would imply E1 prime inverse is the same matrix. This you should check. We have in fact seen that if you exchange the first and the second row twice, you'll get back the same identity matrix, right? Similarly, E2 prime inverse will also be the same matrix, because if you multiply, if C was the diagonal entry, 1 by C would have come up, which is the same here as minus 1. So this is going to be our E2 prime inverse. And how about E3 prime inverse? E3 prime inverse is again the same matrix as E3. And therefore, we know exactly what this object is. So this is going to be equal to, the first one was 0 1 0 1 0 0 0 0 1 times E2 was minus 1 0 0 0 1 0 0 0 0, and the third one was 0 1 0 0. This shouldn't be 0, I'm sorry, this is 1. This is 0 1 0 0 0 minus 1. So these are precisely the matrices we were looking for. This is our E1, this is our E2, and this is our E3. That's good. Now let's look at what is A inverse. Well, A inverse was, so this is the second part, which has to compute A inverse. A inverse, if you notice, is from here just the product of E3 prime, E2 prime, E1 prime. So A inverse is the product of E3 prime, E2 prime and E1 prime, which is, let's just write it down. E3 prime was 1 0 0 0 1 0 0 0 minus 1. E2 prime was minus 1 0 0 0 1 0 0 0 1. And how about E1 prime? E1 prime was the ones which exchanged the first and the second row. So this is going to be exactly this. Okay, so when you multiply something from the right, some elementary matrix from the right, it is just going to be a column operation. So this is just going to be 1 0 0 0 1 0 0 0 minus 1 times the first and the second column get interchanged. So this is going to be minus 1 0. So the first column now will be this, second column will be this, the third column remains unchanged. And how about this? We can think of this as a row operation from the left. So this is going to be 0 minus 1 0 1 0 0 0 0 minus 1. So this is going to be the inverse of our given matrix. You can check that this indeed is the inverse. You should just get hold of the A, which was 0 1 0 minus 1 0 0. Let's see, 0 1 0 minus 1 0 0 0 0 minus 1. If you notice, this is the first one is identity 0 0 0, the second one is 1, the third entry is 0, 0, 0, 1. Yes, this is indeed the inverse. So we have indeed obtained the correct inverse. So let me put this in green for observing that this is our A inverse. So even in the case of very simple matrices, the computations tend to become a bit tedious, but okay, these are concrete methods with which we will be able to compute a simplified echelon form from the given matrix, in this case, which turns out to be the identity matrix. The next problem deals with the relation between a matrix B and a matrix obtained by realizing B as a block matrix entry. So it will be more clear when I write down the problem for you. Let B prime and D prime be M cross N matrices. With entries in R. So let me just write it down in this manner. M cross N of R. Let's obtain two new matrices. Let B and D be obtained as below. Or let me not say obtained as well. Be the matrices. Let B and D be the matrices given by B is equal to 0 or rather 1, then the remaining entries are 0 in both the column and the row, and there is the B prime here. And how do we get D? D is obtained in the exact similar manner. 0 here, and then there is a B prime here. Okay, so the problem demands us to prove that if you can obtain D prime from B prime by an elementary row operation, then you can obtain D from B by an elementary row operation. So, prove that if B prime can be obtained from D prime by an elementary row, or rather for that matter even a column operation, then B can be obtained from D by an elementary row operation. Further, conclude that if rank of B prime is, if rank of B is say R, then rank of B prime is R minus 1. So conclude from the above that if, so this is, let me call it 2, rank of B prime is equal to, rank of B is equal to R, then rank of B prime is equal to R minus 1. So let's look at the problem once more and try to see what it says. The problem says that you are, say, given two matrices. Okay, so let B prime and D prime was the problem. So suppose B prime and D prime are two M cross N matrices such that you get B prime by applying a row operation to D prime. This problem says that suppose our B is obtained from B prime in this manner, and say D is obtained from D prime in this manner, then we have some other, obviously it will not be the same. The row operations applied to B prime is by an M cross M matrix. Now in the case of B, there will be an M plus 1 cross M plus 1 matrix, which will give the row operation from well, B to D, or rather D to B. B is obtained from B by a elementary row operation. Let's prove this and understand exactly how the solution works. Right, so a solution. So what is the information that we have? The information that we have is that B prime can be obtained from D prime by an elementary. So we'll do the solution for a row operation. The column operation proof will be exactly the same. So suppose E be the elementary matrix. So notice that this is going to be an M cross M elementary matrix such that E, so let me call it E prime. E prime D prime is equal to B prime. So that is precisely what the statement says. B prime can be obtained from D prime by an elementary row operation. We would like to show that D can be obtained, or rather B can be obtained from D by an elementary row operation. Obviously, this elementary operation E prime will play an important role in deciding or finding out what the elementary operation E corresponding to which you get B from D. So we'll see how it works. So recall that B is obtained by having 1 in the first 1 entry, 0 elsewhere in the first row and the first column, and then in the other block there is a B prime. So let us define E to be defined as very similar manner. Let's define it to be ones here, and then this is going to be E prime here. So notice that E is then an M cross an M plus 1 cross M plus 1 matrix. And let's try to see what E times D is. Then E times D is what? So let me just write down in figures what this is. This is 1 zeros here in the first row and first column, and then there is an E prime here, and then there is a 1 and there are zeros here, and there will be a D prime. Okay, so let's see. So I would ideally like to leave it as an exercise for you to check that this is going to get a matrix of this type. This is going to be E prime D prime, which is nothing but E prime times D prime is B prime, which is exactly equal to B. So basically from our elementary matrix E prime, we have defined this particular matrix as is done here in star. Okay, so there is one step which I am now circling in green, wherein I have asked you to check the relevant details. I will just give an indicator of what the check that is needed will look like. This matrix 1 zeros here, and then E prime times 1 zeros here, and then the B prime. This, let's see what the ijth entry will look like. So the ijth entry, the ij entry above will be let's see what happens when I is equal to 1. When I is equal to 1. So that means the first row is being considered in the product matrix. First, let's see what happens. So when j is equal to 1, then the 1 entry is equal to 1. and when j is not equal to 1, what will happen? What does that mean? We are considering, I'm putting some j is the column in this part, and when you multiply it to the first row, the first entry is 0 in this column, which gets multiplied with 1 and gives you 0, and the remaining entries here are zeros, which will get multiplied with the remaining entries and which will give you back a 0. So the remaining entries will just turn out to be 0. So hence when j is not equal to 1, 1 comma jth entry is equal to 0. Similarly, when j is equal to 1 and I is not equal to 1, I comma jth entry is equal to 0. So this establishes that in the product matrix, our first row will look like this, and what remains will look like this. The only thing that is to be checked is in the remaining part of the entries. Now the remaining one, again the same argument will tell us that j is also not equal to 1, I is also not equal to 1. So the first entry will not contribute anything. The ij entry, when I is not equal to 1, j is not equal to 1, the ijth entry will just be the ith row of, let's see, the ith row here will be the I minus 1th row of E prime, and the jth column of B prime will be the j minus 1th column of B prime. So this will just give you E I minus 1 k, so let me put a prime here, times B k j minus 1, B prime k j minus 1, which is just the entry, not B, D, which is just the entry B I minus 1 j minus 1. And that's precisely how do we get this entry is equal to B I minus 1 j minus 1? It is because since E prime times D prime is equal to B prime, this will give us this particular entry, and hence the matrix here will just turn out to be equal to the matrix B prime. All right, so we have established the first part of the proof, the first part of the problem. What was the second part of the problem? Let's go back. It's saying that using this first part, conclude that if rank of B is equal to R, then rank of B prime is equal to R minus 1. Okay, so let's see how to go about with this. Let rank of B prime be equal to some k. Let this be equal to some k. But what does that mean? This means that you recall that if a given matrix M cross N has rank R, then you can get hold of elementary matrices E1, E2 up to say EL and F1, F2 up to Fs, such that, so let me write it down. This implies that there exist elementary matrices E1 to ER. Let me not use R, R is given in the problem, so ES and F1 to Ft such that E1, E2, ES times B prime, F1 up to Ft. So let me put primes here. This is equal to an Ik here and the remaining block matrices. So this is going to be K cross M minus K, sorry, N minus K, M cross N it is. This will be a 0 M minus K cross K, and this is going to be M minus K cross N minus K. Now, by what we just proved, this implies that there exists E1, E2 up to ES, F1, F2 up to Fs at Ft at every stage, so that you multiply this E1 to ES, B prime, so B F1 to Ft by putting 1 in the first, 1 entry, zeros in the first row and the first column elsewhere. This will just give you a 1, and then there will be zeros, there will be zeros here, and then there will be an ik. There is a 0 here, there is a 0 here, there is a 0 here, this matrix. But what is this matrix? This is nothing but ik plus 1, 0, 0, 0. Just to be careful about what we are writing, this is going to be m plus 1, k plus 1 cross n minus k minus 1. No, n plus 1 minus k minus 1, which will be n minus k. Similarly, here this is going to be m minus k minus 1, again m plus 1 minus k minus 1, which will be m minus k cross k plus 1, and this will be m minus k cross n minus k. But what does that mean? This means that rank of B is equal to k plus 1 by the very definition of rank and the theorems that we proved in the relevant week, in the 6th week. But rank of B is already given to us, which is equal to R. This would imply that k is equal to R minus 1, which we had set out to prove. So that completes the second problem. So the next problem is a very important problem which talks about the determinant of a matrix which is given in one such block form. So let's see what the problem is. Problem 3. So let M be an n cross n matrix such that M is equal to A, say k cross k, block matrix it is. So this is a 0 matrix below A, which is of n minus k cross k, and there is a C which is k cross n minus k, and there is a B which is n minus k cross n minus k. So suppose M can be written in this form. So M be in Mn of R be such that M is in this form. So notice that where 0 n minus k cross k is an n minus k cross k matrix with 0 entries, with 0 as its entries. Okay, so then what is the problem? The problem is to establish that then determinant of M is equal to determinant of A times the determinant of B. So we have used this problem crucially in some of the theory that we have developed. So let's give a proof of this. So let's see how this particular statement can be proved. So notice once more that our M is in a block matrix form. So the proof is by induction. So let us prove this by induction on K. What was K? K was the size of the matrix A here. So we will prove it by induction on this K. So when K is equal to 1, let's see what happens. M will just turn out to be equal to, the first one will be a 1 here, and then there will be a C here which is, oh, this is not 1, this is going to be A, 1, 1. Okay, let me put it this way. there's an A which is some real entry, and there are A1 to A1k, A, this will be a Z, this will be zeros, and there will be B here, which is n minus k, which is n minus 1 cross n minus 1. Okay, so what will be determinant of M? Determinant of M is equal to, let us look at the cofactor expansion along the first column. This will be A times determinant of B, which is the minor, and the remaining terms will be just 0 times something, and that turns out to be 0. So this is just A times the determinant of B. But what is A? A is the only entry in capital A, and this is hence the determinant of capital A as well, which is determinant of A times B now. So yes, for the case k equal to 1, it's trivially satisfying the condition that determinant of A times determinant of B is equal to the determinant of M. Okay, so let's go further with the induction hypothesis. Assume that the result is proved up to k minus 1. Let's now prove it for the case when our A is of size k cross k. So for the case k, M, then M be equal to, let me write down A explicitly for you. There will be A1k, AK1 to AKK. This will be the first block, right? The capital A. And below will be a 0, which is of the relevant size. There will be a C and there is a B. Okay. So again, let us look at the determinant of M here by looking at the cofactor expansion along the first column. So this will be A11 times the determinant of the matrix first row, and the first column is taken out here for the cofactor expansion. So this will be A22 to A2k, AK2 to AKK. There will be a C prime here. So, okay, so let me do one thing. Rather than writing it like this, I will use the expression we have already used earlier. So this is going to be A11 tilde. There will be some C11 here, which will not be C. The first row will be deleted from this. There will be a 0 here and there is a B here. Okay, how about the second entrant? It will be minus A21 times the determinant of A21 tilde C110B, so on. And what will be the final term? This will be minus 1 to the power k plus 1 times, keep it there, AK1 times the determinant of AK1 tilde CK1. There's a 0 entry here, and then there is the B, which is remaining untouched. Okay, so let's just go up and check what are the expressions which I am now underlining. There are 3 of these ones which I am underlining, and if you notice carefully, these three elements which I have underlined in green, they are going to be covered by the induction hypothesis. I can write this as A11 times the determinant of A11 tilde times the determinant of B minus A21 times the determinant of A21 tilde times the determinant of B, and so on, plus dot minus 1 to the power k minus 1 or k plus 1, whichever is suitable for you, AK1 times the determinant of AK1 tilde times the determinant of B. Now, if you notice carefully, there is a determinant of B here which is common, which is hence equal to A11 times the determinant of A11 tilde minus A21 times the determinant of A21 tilde plus up to a minus 1 to the power k plus 1 a k1 determinant of a k1 tilde the whole times the determinant of b. Now that's interesting because this first term is the determinant of a and then the second term is the determinant of b, and that is precisely what we had set out to prove. So hence we have established the result that determinant of m is determinant of a times b. So the next problem really deals with computing the eigenvalues and eigenvectors of given linear operator. So let's look at it. Let's look at the problem specifically. The problem, was it 4? Yes, 4. So let T from Rn to Rn be given by T of x1, x2 up to xn is equal to, by definition, equal to x1 plus x2 plus up to xn, comma x1 plus x2 plus up to xn, x1 plus x2 plus up to xn. So we have a t which maps to every coordinate is the same, which is basically the sum of xi's. Okay, so the problem is to find the eigenvalues and the corresponding eigenvectors of T. Okay, so let's look at so if you notice in the standard basis, the matrix of T will be a matrix which is given by 1 in every entry. So that's something which you should go back and check. So if the problem is to be rephrased in the language of matrices, so this will be the statement A be the matrix which n cross n matrix where every entry is 1, and then prove, or rather find the eigenvalues and corresponding eigenvectors of this particular matrix. Okay, so for us the language of linear transformations and the matrices have been already noted to be the same through identifying a basis, so it's the same for us. So let's go ahead and see what the solution to this problem is. So what is an eigenvalue? An eigenvalue is a scalar lambda such that there exists some non-zero vector v where tv is equal to lambda times v. So let lambda be an eigenvalue. Then what does this mean? This means i.e. lambda is an eigenvalue means that there exists x1 to xn in Rn such that T of x1, so this is Rn minus, let me just put 0 to denote the 0 element, 0 0 0 in Rn. It shouldn't be a 0 vector, right? The 0 vector is avoided. So this will be lambda times x1 to xn. Okay, let's see what this becomes. What is this going to manifest as? T of x1 to xn is x1 plus x2 plus up to xn, comma x1 plus x2 plus up to xn. This vector, which will be equal to lambda x1, lambda x2, so on up to lambda xn. What does that mean? This means that we have these equations. This implies x1 plus up to xn is equal to lambda x1. x1 plus x2 plus up to xn is equal to lambda x2. x1, there will be n such equations, and this will be the impact. This implies that lambda times xi minus xj is equal to 0 for all I not equal to j. So there are two possibilities here. If lambda is equal to 0, then this equation is satisfied, right? So let me write it like that. The equation star is satisfied for lambda is equal to 0. But what does that mean? This means that t of x1 to xn is equal to 0 times this, right? Which means that x1 plus x2 plus up to xn is equal to 0. This is precisely what it means. So if x1 to xn is an eigenvector for corresponding to 0, or in this case it's just going to be the null space of T, then x1 plus x2 plus up to xn is 0. I'll leave it as an exercise for you to check that. Notice that, or check that, if x1 plus x2 plus up to xn is 0, then T of x1, x2 up to xn is equal to 0. So, which is 0 times x1, x2 up to xn. So, yes, so the eigenspace, let me use that word, eigenspace of 0 is the set of all x1 to xn in Rn such that x1 plus x2 plus up to xn is equal to 0. So, we know that this is an n minus 1 dimensional vector space. Okay, so that is when lambda is equal to 0. If lambda is not equal to 0, let's see what happens then. This would imply that xi is equal to xj for all I comma j. This implies that x1 is equal to x2 is equal to up to xn. And what does that imply? This implies that T of x1 to xn is equal to T of x comma x comma, let's call this equal to say y. This is just equal to T of y comma y, which is equal to y1 plus y1 plus y1 so on. This is going to be ny up to ny, where n is the dimension of Rn, which is equal to n times y. So this gives that lambda is equal to n. So if lambda is not equal to 0, lambda is forced to be equal to n. So hence lambda equal to 0 and lambda equal to n are the only eigenvalues of T. Okay, what about the eigenspace? Eigenspace of lambda equal to n is given by the subspace generated by 1 1 1. So I'll leave that again for you to check. It's straightforward to see that 1 1 1 the vector 1 1 1 is in the eigenspace, and we already checked that if something is in the eigenspace, it will force the coordinates to be equal, and hence in the vector space generated by 1 1 1. So yes, the eigenspace of 1 is the same as the subspace generated by 1 1 1. That we complete the proof. Okay, so I would ask you to think about whether this given matrix T or given linear transformation T is diagonalizable. That's a job for you to think about. Observe that there are two eigenvalues here. Check what is the dimension of the eigenspace corresponding to 0. Get hold of some vectors there. look at what is the eigenspace corresponding to 1, get hold of a vector and think about whether this particular linear transformation is diagonalizable. The next problem will deal with the eigenvalues and eigenspaces in infinite dimensional vector spaces. So this is an exercise, or this is a problem to exhibit that these notions are studied in infinite dimensional vector spaces as well. So let's look at what the problem is. So find all eigenvalues of the linear transformation T from R infinity to R infinity given by, this is the left shift operator. If you recall what that is, T of x1, x2, dot, 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 dot. So R infinity was the space or the vector space of all sequences, x1, x2, and so on. And what was this map? Let me again define it for you. This is just x2, x3, and so on. So find all eigenvalues and the corresponding eigenvectors. So maybe I'll put it here, and corresponding eigenvectors. Okay, so what will be an eigenvalue here like? So the eigenvalues of solution. So let lambda be an eigenvalue. Let's try to see what will be the properties that lambda will satisfy. Then and x1 to x1, x2 be an eigenvector. Let's see what that means. Then P of x1, x2, and so on is equal to lambda times x1, x2, dot, 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 dot. That's precisely what it means. But what is T of x1, x2, and so on? This implies that x2, x3, so on is equal to lambda times x1. So I'll put it inside. This is lambda x1, lambda x2, and so on. And we do a component wise equating of the terms here to obtain x2 is equal to lambda x1, x3 is equal to lambda x2, which is equal to lambda square x1. Similarly, xn or rather xk is equal to lambda to the power k minus 1 times x1. So this forces the eigenvectors to be, so for any lambda, hence for any lambda in R we have, so lambda in R, let me put R minus 0, we have T of let's see, x1, x, lambda square x, and so on is equal to lambda times x, lambda square x, and so on. So every real number hence turns out to be an eigenvalue for this particular linear operator T. And what will be the eigenspace corresponding to the lambda here? That will be the subspace generated by these elements. So the eigenspace, i.e. lambda, is an eigenvalue of T, and the, okay, let me not talk about eigenspaces. That's something which maybe I should drop from the problem as well. We'll just be content with computing the eigenvalues here. Okay, so every real number hence turns out to be the eigenvalue of t. Okay, so the final problem is going to deal with the eigenvalues of the linear transformation on the n cross n matrices which sends a matrix A to its transpose. So problem. I'll put a problem the new problem in a new page. So let T be a map from Mn of R to Mn of R given by T of A is equal to A transpose. So I'll leave it to you to check that this map actually is a linear map. So the first problem is to find eigenvalues of T. The second part of the problem is to describe the eigenvectors corresponding to the eigenvalues, just like in the previous case. Okay, let's look at a solution. So what is the map T doing? The map T is taking a matrix and sending it to its transpose. So we have to find the eigenvalues of T. So let lambda in R, or let lambda be an eigenvalue. We don't know yet whether it has an eigenvalue or not. Let lambda be an eigenvalue. There exists a non-zero matrix. That means at least one of the entries is non-zero, capital A, such that TA is equal to lambda times A. But what is TA? TA is just equal to A transpose. Let's do one thing. Let's apply TA once more. Then T to A transpose. Then T of A transpose will be equal to T of lambda A, which will be lambda times T of A. But recall that to begin with, A was an eigenvector corresponding to lambda. So this is going to be lambda square times A. And what is going to be T of A transpose? This is going to be A transpose, the transpose of that matrix. So what is the transpose of the transpose of a matrix? I'll give you back the original matrix that we began with. This implies that A is equal to lambda square times capital A, or lambda square minus 1 times capital A is equal to 0. But by equating it to 0 component wise, what we will be able to conclude is that lambda square minus 1 is equal to 0. And this forces lambda to be equal to 1 or lambda to be equal to minus 1. So the only possible eigenvalues of the operator T here will be 1 or minus 1. Let's see what happens when lambda is 1 and what happens when lambda is minus 1. So if T of A is equal to 1 times A, this implies that A is equal to A transpose, which is i.e. this means that the matrix is a symmetric matrix. This is what is called as a symmetric matrix. Okay, and what will happen when T of A is equal to minus of A? Lambda being minus 1 here. This implies that A transpose is equal to minus of A. So this implies that Aij is equal to minus of Aji. So this will turn out to be the eigenvectors corresponding to minus 1. So it's a good exercise to sit down and check what the basis for the eigenspace corresponding to 1 will be and what will be the eigenspace corresponding to minus 1 will be. Okay, let me stop here.